Hello and welcome to section 6.2. In this section we are going to be dealing with differential equations for growth and decay. And so our first example is we kind of just need to talk about what's happening here. And so they gave me this differential equation and we're solving it. So basically we're trying to find the solution for this guy. And so we know that we are given the rate of change, which is dy over dx equals 2x over y, and so then I could multiply both sides by y, and to remove the y, and so I end up with times y, and so I have y dy over dx equals 2x, and then if I multiply basically by dx on both sides, I would get y dy equals 2x dx. So I basically went through and kind of separated the variables, and now if I integrate both sides, I can get a solution for this, and the integration of y is going to be y squared over 2 equals, and over here it's going to be 2x squared over 2 plus c, and then if I solve this, for the best I can do is multiply by 2 and kind of move the x over to the side, and I'm going to end up with y squared minus 2x squared equals c. And so that's just a little algebraic jump from here to there, but this is the solution, and it's a general solution because we don't know what c is. We weren't given any initial conditions. So then we're going to talk about exponential growth and decay, and in this one there's just some things that we need to know. When we're given that y is proportional to another function, we end up with this, that y prime, the rate of change, is proportional to another function. We get something that looks like this. And so c again is our initial value like always, k is our proportionality constant, and we'll be dealing with exponent. If k is greater than 0, it's growth. If k is less than 0, it's decay. So we're just kind of reminding you of things that you learned in pre-calc. This formula right here is the same as PERT that you're used to seeing, but we'll deal with that as we go along. So then, this time, again, we are given that the rate of change of y is proportional to y. So that would mean the equation I just showed you, that y prime is equal to k times y. So if we were to integrate this and kind of work our way through this, we would end up, this thing is going to be with respect to time, and so I'm going to end up saying, okay, well, this is y dy over dt equals ky. And so that means I'm going to divide by y, and so I'm going to be left with 1 over y dy equals k times dt. Now I will go ahead and integrate these with respect to y on this side and t on the other, and so that gives me an equation of something like, well, you got to remember that this is the natural log integration, and over here I'm going to pick up a t, so it's going to be t times k, and then plus c. Well, now if I want to remove the y value, the natural log, to just get y, remember I do a base e. So I do a base e all the way across here, basically, and I end up with the equation that y is equal to e to the k times t, and then there's this plus c, but remember what we do with same bases, and when we add the powers, they end up multiplying, so we get a function that looks like this. So this is our basic exponential growth or decay model, and so now we can go ahead and kind of work through this problem. So they told us that when t is 0, y is 2. So that would mean that if t is 0 here, I could go ahead and plug that in and say, oh, well, 2 equals c e to the k times 0, which k times 0 is 0, e to the 0 power is 1. So basically, we know that c is 2. And so then, with that being the case, we can say, oh, well, we could kind of plug that into the equation that we were just given and say y will equal 2 e to the k t. Now if we look at, it says when t is 2 and y is 4, then we know some more information and we can help us find k. So basically for all of these problems, you're not going to have to go through and integrate to get to this. You should already be able to just jump straight to this equation, but you're going to have to take the two conditions that were given, for example these two guys right here, and make sure that you can get the k and the c value out of it. And so that's pretty much the work every time, is you're going to have to find c, you're going to have to find k, and then once you find those, then you can use the particular equation that they want, and that will help us as we go. So we're going to find k now, and so they told us t was 2, they told us y is 4, so I plug those in, so 4 equals 2 e and the k times 2. So now we have to do a little work. If I divide by 2, I get 2 equal, did I just put those in right? Yeah, 2 equals e to the k times 2. And so then I can go ahead and natural log both sides of these just to get rid of the base e. So if I natural log both sides, I get ln of 2 equals k times 2. And then I will divide by 2, so 1/2 ln of 2 equals k. And if that's the case, then that's my k value, that's my exact k value, which is approximately 0.3466 when I calculate it out. So now to find what 3 is, what's happening when t is 3, I will go back to this whole thing and say y equals, I know c is 2, I found that, e, because my goal is what is y, I'm going to put in the exact value for k, well actually I'll put 0.03466 and multiply it by a time of 3, and when I crunch those numbers in my calculator, I end up finding out that it's 5.657. And so that's really all we're trying to do for these examples. And if you have any questions, please come to class prepared to ask them. Thank